our second lesson on inverse functions. We are going to continue on. This is part 2. In this lesson, we are going to be able to determine if a function is one-to-one, and then we'll be able to find the inverse of a one-to-one function. And the reason that one-to-one is important is if a function is one-to-one, then it has a unique inverse. So that's how it ties into relating to the topic of inverse functions. Okay, so one-to-one function. A function is one-to-one if for every element in the domain there is only one element in the range. So this differs a little bit from the definition of a function. Another way of saying this is if we have f of a equals f of b, it means that a is equal to b. Okay, we won't really use that very much. That's more of a mathematical definition. Okay, so example 1, determine if the following functions are one-to-one. Okay, so they are functions. Notice here we have in the domain we have -2 going to 4, we have -1 going to 1, 0 going to 0, so we're okay so far. But now we have 1 also going to 1. So this means that for this element in the range, there's 2 elements in the domain. So this makes it not one-to-one. Okay. If we look over at part B, we have -2 going to -8, -1 going to -1, 0 going to 0, 1 going to 1, 2 going to 8. So for each element in the range, there's only one corresponding element in the domain. So in this case, part B, this is one-to-one. Let me spell that right. Okay. Another way that we can determine if a function is one-to-one is from the horizontal line test. So this may sound a little bit familiar because before we had something called the vertical line test. And the vertical line test told us if a given relation is a function or not. So we were given the graph of some type of relation, we drew vertical lines, and if it only touched the graph of the relation once, then it was a function. Now what we're going to use is called the horizontal line test, and this is going to tell us if a relation is one-to-one. So what we do is we draw horizontal lines through the graph, and if the horizontal line intersects the graph more than once, then the function is not one-to-one. If it intersects the graph one time for each line, then it is one-to-one. Okay, so example 1 continued. So taking example 1, I took the points -2, 0, -1, 1, 0, 4. The domain and range, I made them into ordered pairs, so we could use the horizontal line test as well. So if we draw horizontal lines, okay, it intersects here 2 times, so this would not be one-to-one. Okay, if we look at B, if we draw horizontal lines, okay, the horizontal line intersects only 1 point, so this is one-to-one. So determine whether the function is one-to-one. So we're given f of x is equal to 3x cubed plus 8, and we are able to estimate the graph of this function. So you can pull in function transformations, which is what I'll talk about. You can also pull in end behavior and multiplicity. Some of these, it may be easy to find the zero, some of them it may not. So remember that the graph of y equals x cubed looked like this. Okay, so this plus 8 means that it goes up 8, and this 3 is a vertical shrink, not a shrink, a stretch, vertical stretch, which means that it's going to move away from the x-axis. So we can go up 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then it's going to be a little bit more scrunched towards the y-axis. Okay, so the purple is an estimation, and then if we draw horizontal lines, each horizontal line intersects the graph only once. Okay, now I'm only looking at the purple. The black was just a reference of y equals x cubed so that we could graph f of x. Okay, so yes, this one is one-to-one. Example 3, determine whether the function is one-to-one. So we have f of x is equal to x squared minus 5. Picture the graph of x squared, the U-shaped graph. We've got a vertical shift down 5 units. So this is going to look like something like this, and then we apply the horizontal line test. Intersects twice. Okay, it's going to be a problem throughout. You only need one horizontal line that intersects the graph more than once to determine whether it's one-to-one or not. Okay, so in this case is no. I just drew more lines to show various examples depending on where you started your lines. Okay, example 3, oops, this should say 4. Okay, use the horizontal line test to determine if the function is one-to-one. So in this case, the graph of each function is given to us. So in part A, we have f of x is equal to 2.3 raised to the x power. If we draw our horizontal lines, it's intersecting the graph only one time. I know it may not look like it here, but if you were to zoom in, this is just getting closer and closer to the x-axis, but it would still pass the horizontal line test. So this is yes. For part B, we draw horizontal lines. It intersects the graph twice. This would be a no. So finding the inverse of a function. So a function has a unique inverse if it is one-to-one. So that's why we just spent time talking about and being able to determine if functions are one-to-one or not. Okay, so if we have a function and it's one-to-one, it has a unique inverse, and its inverse is also a function. Now the notation here, if we have f of x, its inverse is denoted by f minus 1 of x. Okay, so we're not raising it to the negative first power. It does look like an exponent there, but think of that negative 1 as an inverse when we're dealing with functions. Okay, and our steps to find the inverse. So we replace f of x with y. Remember, f of x is equal to y. We interchange x and y, which is what we had talked about in the first lesson about what an inverse is, as we're interchanging the input and the output. Solve for y. Once we have it solved for y, now what we're going to do is replace it with the inverse notation. Okay, so let's look at a couple of examples. So example 1, determine whether the function is one-to-one. If it is one-to-one, find its inverse function. So first, let's graph this to determine if it's one-to-one. This is a line. Our slope is 1, and our y-intercept is negative 5. 1, 2, 3, 4, 5, up 1 over 1. Okay, so we've got a line. And you may know that a line is one-to-one without graphing it. Okay? And if you do the horizontal line test, it would pass. So now let's find its inverse function. So the first step is to replace f of x with y. The second step is to interchange x and y. The third step is to solve for y. So I'm going to add 5 to both sides to get x plus 5 is equal to y. And then the fourth step is to replace y with f inverse of x. So the inverse of f of x equals x minus 5 is x plus 5. Example 2, determine whether the function is one-to-one. If it is one-to-one, find its inverse function. Okay, so we have f of x is equal to 7 over x plus 9. So again, we can graph this. Okay, so I'm just going to draw a sketch. Remember that the graph of 1 over x looks something like this. So now we are going to have, so the 7 is a vertical stretch. It's going to move it away from the x-axis, and that negative 9 is a horizontal shift to the left 9 units. So we go to the left 9 units, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and so it's going to turn out to be something like this instead. But if we apply the horizontal line test, it would still pass. So yes, this function is one-to-one. Okay, part B, if it is one-to-one, determine its inverse function. So step 1 is to replace f of x with y. Step 2 is to interchange x and y. And then step 3 is we are going to solve for y. So in this case, what we have to do is we treat it like we're solving a rational function or a rational equation because we've got our variables in the denominator. There's a few different ways you can think of this. I'm going to rewrite it. 7 over y plus 9. You can think of it as a proportion where you cross multiply. You can think of it as getting the same denominators, or we can multiply the common denominator to each side, which is what I'm going to do. So I'm going to multiply both sides by y plus 9. So on the left-hand side, I have x times y plus 9 is equal to, now division by y plus 9 and multiplication by y plus 9 causes those both to cancel out. So that's equal to 7. And now our goal is to solve for y. So on the left-hand side, I'm going to distribute everything. So I have xy plus 9x is equal to 7. Okay, and now we solve this like we would an equation with many variables. Our goal is to solve for y, so we first need to subtract 9x from both sides. So we have xy is equal to 7 minus 9x. Those don't combine because they are different terms. Okay, and then the last step here to get y by itself is to divide both sides by x. So we have y is equal to 7 minus 9x over x. And then the fourth step is to replace y with our inverse function notation. So a lot of steps for one problem. Example 3, determine whether the function is 1-to-1. If it is 1-to-1, find its inverse function. Okay, so we've got the graph f of x is equal to the cube root of 4x. We talked about our cube root graph before. It looked something like this. And we apply transformations where this is going to get closer to the y-axis. Okay, so it's probably going to do something more like this. Okay, if you apply the horizontal line test, this would pass. So it is 1-to-1, meaning we can find its inverse. Okay, so the first step is to replace f of x with y. The second step is to interchange x and y. And the third step is to solve for y. Okay, so I'm actually going to go to the next slide. So we're taking a cube root. So in order to get 4y by itself, we can raise both sides to the third power. It's kind of like when we were getting rid of square roots, we were squaring both sides. The same principle is applying here. So we raise both sides to the third power. Okay, so we have x to the third is equal to 4y. Okay, the cube root times itself 3 times is going to cancel out the root and just give us 4y. And now we divide both sides by 4 to solve for y. And the last step is to replace y using our inverse function notation. Okay. So we have the inverse is equal to x cubed over 4. Thank you for watching. If you have any questions, feel free to reach out to me.